Howdy and welcome back. So we're going to introduce a pretty cool data structure in today's lesson. It's going to be a binary search tree. And in doing so, we're going to expand upon the binary tree that we introduced within the previous lesson. Therefore, it makes sense to go ahead and begin with a review of binary trees. But I'm going to go ahead and, put a bit of a spin on it in this lesson to hopefully help clarify some of the different components of what we'll be discussing. So I'm going to say that a node is not only going to store some sort of data, but our node is also going to store some sort of key value, which would say uniquely identify the data contained within a respective node. For instance, maybe we have, this within this binary tree showed here on the right, we're storing a bunch of student objects. So in that case, the data would be of type student. So T1 would be student. The key could say be a UIN, so that might be a long integer. And we were searching for a particular student within this tree, and we'll get into searching here momentarily. We could simply search for the node whose key value is the student's UIN. So we'll go ahead and get into this in a bit more detail as we're progressing through, but I did want to separate out our key from data. Now, if you remember what makes a binary tree, it's that it is going to have at most two children. How do we connect up, say, the root of our tree, one node, or any node for that matter, to its children? Well, we're going to go ahead and say that each node is going to have a left pointer, which will point to its left child, provided it has one. And then we'll have an additional node, right, which will store the address of the node to that node's right. And as we go through this, you can see that a tree is going to begin to emerge. So we're having some sort of hierarchical ordering of this data. And you can see that with each level, we kind of branch out further. And if you were to flip this, upright, you begin to see something that looks like a tree. Cool. So one other thing to just keep in mind here is that our trees do have a pointer, the nodes contained within our trees do have a pointer to their parent. In the case of the root, remember that's kind of the node that starts it all is not going to have a parent. However, all of the root's children and the children thereof, etc., will all have a pointer back to their parent node. So we said here, if we're looking at the root node, we could say that this node is the parent of these two children nodes. And notice here that not only does the parent point to the children, but the children are pointing back to the parent. So what are binary search trees? This isn't going to be that much of a leap forward, but we're going to see here that a binary search tree is going to be an organized binary tree that's going to be represented using a linked data structure as we've seen literally just now on this slide. Each node is going to contain some sort of key and data. We just covered that, key and data, with our student example, along with pointers to the node to its left and right, and also to its parent node. We drew this up, so far, there's really nothing new. We said that if a child or the parent node is missing, the respective pointer points to null pointer. And again, binary tree means at most two children. So it could have a node could have 0 children, 1 child, or it could have 2 children. Now here's what makes a binary search tree a binary search tree and not just a plain vanilla binary tree. The nodes in a binary search tree are going to be arranged to satisfy what we're going to call the binary search tree property. So let X be any node in a binary search tree. If Y is a node in the left subtree of X, so if we look up here, remember that we said that, here, let's use this node here as an example. Let's say that we're looking at this. We would say that node's left subtree is all of this. That node's right subtree is all of that. So left subtree, right subtree. So if Y is a node in the left subtree of X, so over here, in a binary search tree, that is going to imply that Y's key value is less than X's key value. So let's say that this node maybe stored the value 10 as its key value, every node presenting in the left subtree would have a key value less than 10. So this could be something like, let's go with 5. Now, if y is a node in the right subtree of x, then y's key value is going to be greater than or equal to x's key value. So if we look over here, this would have to be in the right subtree. The key value of this node right here is going to have to be greater than that of its parent. So it could be something like, let's call it 15. And as we continue this process, for instance, okay, 10, its left subtree has a key of 5. Well, let's look at 5's right subtree. It's going to have a key value that is between 5 and 10, with 10 being not inclusive. So in that case, we could have any of the values from 5 to 9 stored within it. So let's go ahead and go 7. 7 is less than 10, but greater than 5. Now, let's go ahead and consider 7's left subtree. It's going to have a key value that is greater than 5, but less than 7. So that could be, I don't know, 6. Hopefully y'all can read this. Now, if we come up here and we look at the right subtree of the node containing the key value of 10 and get down into, say, that containing 15, so we're back over here, the node in its left subtree must be between 10 and 14 inclusive, right? So it could be the value, let's say, 12. So let's go ahead and kind of look at some of the implications of this here. If we were to step to the right of the root, or excuse me, of the subtree containing the right subtree of the root, and then step to the right of this node right here, you'd expect all of the values to be greater than or equal to 10. If you step to its left, you would expect all of the values to be less than 10. And of course, whatever the root node's key value is, greater than or equal to that value. So hopefully you kind of see the ordering that this is placing within data within our binary search tree. So again, the binary search tree property is simply saying, okay, let X be a node in the BST. And this is kind of recursive, so starting from the root down, right? So each kind of subtree has to go ahead and respect, say, it's kind of the tree that it's a part of, the ordering the binary search tree property for the entire tree. So if X is a node in the BST, our binary search tree, if Y is a node in the left subtree of X, then Y is going to have a key value that is less than X's key value. If Y is a node in the right subtree of X, Y is going to have a key value that's greater than or equal to that of X. So let's go ahead and we kind of drew this out, but let's look at some additional ordering here too. What we're going to see here is that both of these are valid binary search trees. They're both going to respect the binary search tree property. For the case of the tree over here on the left, we can see that, okay, we have a root value of 6. Its subtree is going to have all values less than 6. If we go ahead and look at its right subtree, we can see here that all of those values are greater than or equal to 6. And notice one of the kind of cool properties of this particular tree. There are, let's go ahead and count the nodes, 1, 2, 3, 4, 5, 6 nodes in this. And notice how if we take a step either to the left or the right of the root, we've essentially kind of halved the number of nodes that we'd have to look in if we were looking for a node with a specific key value. We're going to see that this kind of property here, this balanced tree, is going to be a very desirable representation, more so than the unbalanced tree shown here on the right. Notice here, like if we take a step to the right, I mean, up through kind of this whole thing, we're almost dealing with kind of a, singly, or I guess a doubly linked list in this case, where by taking a step to the right, we're not really getting any closer to a particular value that we're looking for, right? We're not ruling out some huge, large number of nodes as we did in the example on the left. Let's go ahead and look at this. So what we're going to see here is there's very profound implications in how we're going to construct these trees in this class. We'll see in 225 that there is a way to create self-balancing trees that are going to kind of keep the representation of what we're seeing in the left example here, while avoiding the representation that we're seeing on the right side. Because again, this right representation is almost kind of starting to look like if you actually look at it, it's a lot of the nodes are almost within this doubly linked list representation. And the only place we can actually branch is at node 7. But we're not going to worry about balancing these within this class. But again, the key takeaway here is the left and the right are both binary search trees. The values to the right of the root node are all going to be greater than or equal to 2. We can see here that when we look at the next node within our tree, so at the next level, the next depth, looking down one, we can see here that all the values to the right of the node containing the key value of 5 is going to be greater than or equal to 5. And then we look at the node that's hooked up to 5's right, we see it's 7. Okay, so that's still respecting our binary tree property. Notice that to the left of 7, all of the values are less than the key 7. We see 6, and to 6's left, 5. And again, just looking at this, when we look at the tree as a whole, the binary search tree's property is going to be maintained here. And then if we were to look to the right of 7, we see, again, that property is maintained. So I hope at this point you kind of can see here what the binary search tree property is and what a binary search tree is compared to, say, a plain vanilla binary tree. So binary tree, again, just some sort of tree structure that has at most 2 children. Binary search tree, it's a binary tree where this property, the binary search tree property, is satisfied. So this is going to be a little bit of review on this slide. So a binary search tree that contains no nodes is going to be called the empty tree or the null tree. Take your preference. These terms mean one of the same. If you recall from the earlier lesson, the height of a binary search tree is going to be defined exactly how we define the height of a binary tree, as simply the length of the longest downward path, so number of edges, to a leaf from whatever node. And the overall height of a particular binary tree, so the whole tree, would be the longest path to a leaf. And then we also define this idea of depth, which was essentially top down. So the root would start out at depth of 0. Each kind of additional edge away from the root, we'd increase the depth by 1. And then we said the height is bottom up. Remember, a leaf has a height of 0. And as we begin moving up, we can see here to this node right here, the longest path to a leaf is 1, 1. So that node's height will be 1. And continuing this process, we can see that that would be 2, and that would be 3 in terms of the overall tree's height. Okay, so we're not going to get too much into this, but we're going to define what it means for a binary search tree to be considered height balanced. A height balanced binary search tree is simply going to be one where the height of the left subtree minus the height of the right subtree, the absolute value of this difference, is less than or equal to the integer value of 1. So we can see here 2 examples of height balanced binary search trees. If we look at the height of the case on the left example, we can see in both instances we have a height of 2. So that would satisfy what it means to be a height balanced binary search tree. Likewise, if we go ahead and look at the example to the right, the left subtree here will have a height of 2. That on the right will have a height of 1. 2 subtract 1 is going to be less than or equal to 1. So that would be a height balanced binary tree as well. Notice that if we just had 19, let's say this example, oops, that's not following our binary search property. Trying to do this too fast. Let's go ahead and say that's 7, and then that's 24 as before. Notice here the height difference here is going to be 1, 2, 3. 3 minus 1 is 2. So that would not be a height balanced binary tree. So continuing on here. There are, and this will be the last slide for this section, there are self-balancing trees, as I've kind of alluded to. You'll see AVL trees, red-black trees, likely in 225, and they're all going to favor something that is height balanced, and they'll, such as the example here on the left, and they'll avoid something of this non-balanced tree shown on the right. So with all of that in mind, let's begin talking about different ways to traverse these trees to visit the nodes.